So first, databases allow data to be easily accessed, managed, modified, updated, controlled, and organized. Unlike simple files, databases provide built-in mechanisms for data integrity, user access control, and concurrent operations. Multiple users can work with the same data simultaneously without conflicts, and the system ensures that data remains consistent and accurate. Most databases use structured query language, or SQL, for writing and retrieving data. SQL is incredibly powerful because it allows you to express complex data operations in a relatively simple English-like syntax. For example, you could write an SQL query to find all customers who have loans over $100,000 and have made late payments in the past 6 months. A query that might be very important, for example, in risk assessment. SQL serves multiple functions. It's used for querying data, so asking questions of your database, manipulating data like inserting, updating, and deleting records, defining data structures like creating tables and relationships, and providing access control, determining who can see or modify what data. For AI applications in risk management, SQL's power becomes evident when you need to prepare training datasets. You might need to join customer information with transaction history, loan details, and external credit data. SQL makes these complex data preparation tasks manageable and efficient. The standardization of SQL across different database systems also means that skills and queries are transferable between different platforms, making it easier to work in diverse technical environments. Now, the database landscape includes many different types, each designed for specific use cases and requirements. Understanding these different types help you choose the right tool for your risk management and AI application. First, we have legacy databases, which are based on older technology and are rarely used for new applications today. You might encounter them in established organizations. These include network databases that we'll explore in detail in a few minutes. Relational databases became dominant in the 1980s and remains most common today. They organize data in tables with rows and columns and use SQL for data manipulation. This includes platforms like Oracle, SQL Server. And then we have object-oriented databases. They store data as objects, similar to object-oriented programming languages. While not as common as relational databases, they're useful for complex data types like multimedia content or sophisticated financial instruments. Distributed databases spread data across multiple computers or locations. This is increasingly important for large organizations that need to manage data across different geographic regions while maintaining performance and compliance with local regulations. Data warehouses are specialized databases designed for analytical processing rather than day-to-day transactions. They're optimized for the complex queries and large-scale analysis that are common in risk management and AI applications. Multidimensional databases are designed for online analytical processing and are particularly useful for financial analysis and reporting. NoSQL databases handle unstructured or semi-structured data and are designed for web-scale applications. Graph databases specialize in managing relationships between data entities, which can be valuable for fraud detection and network analysis in risk management. Let's start with legacy databases. Even though they're not commonly used for new development, but at least you'll be familiar with them. Understanding them is still important because you may encounter them in established organizations, and some of their concepts have re-emerged in modern forms. Legacy databases are based on older technology. However, many large organizations still run critical systems on these platforms, so you might need to integrate with them or migrate data from them. There are two major types of legacy databases. Hierarchical databases. They use hierarchies or inverted tree structures to represent relationships between data. In this model, each record has one parent record and can have multiple child records, forming a tree-like structure. Think of hierarchical databases like a company organizational charts. The CEO is at the top, with vice presidents below, then directors, managers, and individual contributors. Each person has exactly one boss, which is a parent, but might supervise multiple people, the children. In risk management, you might see this structure used to organize geographic data, like countries that contain states, and states contain cities, cities contain branches, and branches contain customers. While this works well for strictly hierarchical relationships, it becomes problematic when relationships don't fit neatly into a tree structure. Network databases are collections of records related to each other through pointers. Unlike hierarchical databases, network databases allow records to have multiple parent and child relationships, forming a more flexible web lab structure. While these legacy systems seem outdated, their concepts have influenced modern database design. For example, XML databases use hierarchical structures, and graph databases are very similar to network databases. Let's dive deeper into hierarchical databases to understand their structure and limitation. So, in this type of databases, we organize the data into a tree-like structure where each record has exactly one parent record and potentially many child records. The data are stored as records connected through links, with each record being a collection of fields containing single values. These structures work well when your data naturally fits into a hierarchy, but it can be limiting when relationships are more complex. A record is a collection of fields, with each field containing only one value. For example, a customer record might have fields for customer ID, name, address, and phone number. The hierarchical structure then determines how these records relate to each other. These databases are primarily used today for storing geographic information file systems. Your computer file system is actually a hierarchical database because you have folders that contain subfolders and files, forming a tree structure where each item has exactly one parent. An example of a modern database is RDM Mobile. These databases have resurfaced as XML databases, which use a tree-like structure to organize data elements. In risk management, you might encounter these databases when dealing with organizational data like headquarters to regions to branches to customers, or product hierarchies like asset class to product type to specific instruments. However, the rigid parent-to-child relationship can be problematic when customers have accounts at multiple branches or when products don't fit exactly into one category. So you can see here a diagram with a typical tree structure with a root node at the top, level 1 children below it, and then level 2 children at the bottom, illustrating the strict hierarchical relationships that define this database model.